Very easy. Okay? You will see a similar problem in your exam. Always give you a problem like that. You will see it from practice exams, right? So, how are we going to do it? 1, 2, 3, 4, 5. Corners and end of line. So how many carbons? 5. Hydrogens, how many hydrogens? Let's see. 1, 2. So these missing ones are what? Hydrogens, right? So there's 2 here. 1, 2, around this carbon. You see these are carbons, right? So around this carbon, 1, 2, 3, 4. Right? 1, 2, 3, 4. 1, 2, 3. Only 1 here. 1, so you have actually 3 hydrogens here. Right? So you have what? 2 times 3, 6, 7, and 3, 10. See how easy it is? Pretty fun, huh? C5H10. Okay. How about this one here? How about to balance this reaction that is... Okay, so what does this problem tell us? It's telling us to balance the chemical equation for the complete combustion of this organic compound, which is carbon, hydrogen, and oxygen in there. Okay? So you are combusting it. By definition, when you combust some organic compound, what do you do with it? You're burning with what? Oxygen. You react with oxygen, right? And when it says complete combustion, that means that the whole compound is converted into carbon dioxide and water. That's the definition. Okay, combustion, the reactant is oxygen. Complete combustion, the whole chemical compound is turned into what? Not carbon monoxide mixture with CO2, no. Just carbon monoxide and water. So, you know what to write down, right? So you write down what? You write down this thing here. Plus oxygen will give you CO2 and water. And you want to balance it. Well, if you start balancing this equation, it's going to be not easy. The way it is. It's a very simple equation, but the way it is not going to be easy. So you always put the molecular formulas in a condensed form. That means all the atoms of each element together. Yes? So what you will do is you will say, okay, how many carbons do I have? 1, 2, C2. How many hydrogens? Or how many oxygens? 2 oxygens. How many hydrogens? 6. Okay? So now, you write your equation in this way. Now if you are ready to do it. Otherwise, you will waste your time trying. Right? Try to do it. Half a minute. It's scary. Okay, so we start with the very complicated formula first, in this kind of equations, combustions always. So I have two carbons. We have, you see, we don't want to do oxygen now, because oxygen is 2 or more compounds, right, or substances, right? So we don't want to do the oxygen. We do the elements that are in one only, possibly, chemical species in each side. So hydrogen is in one here, and only in one here, yes? So I go to hydrogen now. So I have how many? 6, therefore I will put 3 here. Now I have 6 hydrogens. By doing this, I have balanced already this side. Therefore, that means that the oxygens already are balanced. How many there are? They are balanced. We know the number of oxygens in the right side, correct? So how many there are? 4 and 3. 3 times 1, 3. 7. Right? 7. Now, if you are in a hurry and you're going to say, okay, 7.5. 7.5 times 2 will make 7. What do you will not get the right answer. because we were 2 in a hurry, right? Because they have to be here total 7, and here is 7, right? If you want to be here total 7, you better don't forget that one. Yes? This is already 1 because you used as your reference, your starting point, right? So it's 1 there. So you have 2 options. If you want to be 7, this has to be how many? How many from here? 5. So you will have to put here 5.5 to make it total 7. Yes? So the answer should be what? Well, if you don't want ratios, right, then you will have to multiply by what? By 2. So you will have 2 C2 O2H6 plus 5 O2 will give you what? 4 CO2 and 6 waters. If you don't want to have ratios, just integers, right? So the answer should be E. How about this one? How about this has to do with objection numbers? To arrange in a way of increasing algebraic increase, because you see oxidation numbers are plus or minus, right? Algebraic numbers. So we're talking about an algebraic increase. From minus to plus to 0 through 0 to plus, right? If you want to arrange them, you will have to find each one of them. Otherwise, really you cannot do it. So let's do that, right? So how about zinc oxide? How much is going to be the oxygen there? What's the oxidation number of oxygen there? Zinc oxide is an ionic compound, metal, non-metal, right? Ion. So what will be the oxidation number of oxygen? It will be its charge. And because this is neutral, 0, formula unit, zinc oxide is neutral as a formula unit. This is metal, this is the non-metal, oxygen. In this case, we will never have O minus 1. You remember, as an ion, never. And therefore, you will not have, in this case, that kind of case. So, what's the oxidation number of oxygen here? It will be its charge. What's the charge? If those is 0, and zinc is always what? Plus 2, then oxygen has to be minus 2 charge, right? 2 minus, we put it, 2 minus. So, the oxidation number will be? The oxidation number will be? Minus 2. Not 2 minus, minus 2. We're talking about oxidation numbers. If you want to talk about charge, you will say 2 minus. Now, if you want to talk about oxidation numbers, you will say minus 2. Yes? Okay, so minus 2. How about the other one? So minus 2 here. How about potassium? Oh, that kind of thing is called superoxide. Pretty weird stuff. Potassium superoxide. So in this case, it's very difficult to do it because you know potassium is always, it's an ionic compound, the whole thing is 0. And potassium is always what? Plus 1. And so O2 will have what charge? What's the charge of O2 here? Minus 1. Minus 1 is the charge. So what's the oxidation number of oxygen? Which will be an average oxidation number, because we talk about the oxidation number of averaging the oxidation numbers of 2 oxygens. So what's the oxidation number of oxygen there? So these 2 are charges, right? Charges, look, charges. Charges. This and that, they're charges. Potassium plus O2 minus 1. Here is 1, here is the other. These are the charges of these ions. But we want oxidation number. So what's the oxidation number of oxygen? It will be a number x times 2 will give you minus 1. Isn't that right? Whatever the oxidation number of oxygen is, we don't know, times 2 will give you the charge, which is minus 1. Yes? So the oxidation number of oxygen, X, oxidation number of oxygen, average oxidation number of oxygen is equal to minus 1/2. So I'm going to put here minus, for this oxygen there, we'll put minus 1/2. You guys get it? You got it? How many people say no? Let me see your hands. No? You say no? Did you get it? How many people did not get it? Let me see your hands. Are you serious? What's going on? Martin, you have to wait a little bit, right? We don't understand oxidation numbers, so we got to delay a little bit. You agree with that? Yeah? Look, potassium superoxide. It's called superoxide. And you want the oxidation number of oxygen. The oxidation number, as we said, is defined for a particular oxygen, one atom in a molecular polyatomic ion. When you are asked the oxidation number of an element that has a number of atoms in that chemical species, then you're talking about that number that you will say the oxidation number of that element is, if you have more than one atom, is an average oxidation number, okay? So, here is an ionic compound. This is a metal, oxygen is a non-metal. So there is, if it's ionic compound, you know why, yes? You understand that? It's an ionic compound. Then the potassium is always +1 in ionic compound. We said that. Okay, so I have potassium +1, plus, and the other one has to be what? Has to be what? It's a formula unit, it's 0. This is 0 charge. Because it's the formula unit of an ionic compound, 0 charge. If potassium is always +1, this part will have to be what? 1 minus. I can put it just minus, okay? Will be minus. And these are the charges, yes? Oxidation number for ions, in this case, is the same as the charge. Okay, so these are charges. This and that are charges. But the charge is also oxidation number. So, for potassium, oxidation number is going to be equal to +1. Now, here, the oxidation number is defined for one atom in a molecular polyatomic ion. Here, we have more than one. We have 2. It could be 3, 5, 10, whatever. It's 2. So, when I say the oxidation number of oxygen, I mean which oxygen of the 2. So in this case, when we will calculate now the oxidation number for oxygen, the element oxygen, is going to be an average oxidation number of the 2 oxidation numbers of these 2 oxygens. We're not going to talk about now how much is each, because one is 0 and the other is -1. How do I know that? Well, you have to know the Lewis structure. We didn't talk about that yet. But we can find out the oxidation number. We don't need to know Lewis structure to find the oxidation number. Why? Because look, this is the charge, yes? Correct? The charge has to be equal to the sum of the oxidation numbers. Always. When you have an ion, the sum of the algebraic sums of the oxidation numbers of all atoms is equal to the total charge of the ion, or the atomic ion. That's a rule. Yes? You remember that? How many people remember that? Raise your hands. Okay, most people remember that. So, when you have oxidation numbers in an ionic compound or molecular compound, the sum of the oxidation numbers is equal to the charge of the species. So the charge of the species now is how much? -1, and that has to be equal to the algebraic sum of the oxidation numbers. So, the oxidation number of oxygen atom there, each one of them, is X. You do not know how much. How many oxygens do I have? 2. And so this X stands for what? Oxidation number, actually average oxidation number of oxygen. The element of oxygen. The element. Oxygen, the element. You know, you hardly find any general chemistry book to talk about this concept. So that's why our students are always confused. So you go any university and they say, oh, oxidation number is such a magic idea. What is it? TAs, teachers from here to there, talk about oxidation numbers all the time. Why? Because nobody has sat down and make a little bit clarity about this ridiculous simple concept. I have not seen in any general chemistry book. Maybe there is one among hundreds or thousands. There is probably 1 or 2, but it's almost not there. So, the oxidation number, we don't know, X. What kind of oxidation number? We're talking about when there's more than 1 atoms in the chemical species, average. The average oxidation number of the oxygen, the element, in this polyatomic anion is X. We do not know. And according to the rule, right? The sum algebraic sum of oxidation numbers, which is now going to be 2 times x because I have 2 oxygens. 2 times x is going to be equal to the charge of the species, which is how much? Minus 1. Therefore, x from here is going to be minus 1/2. So the oxidation number of oxygens in that superoxide is what? Minus 1/2. About OF2. OF2, which you will call it what? Oxygen difluoride, according to terminology. You will not say monooxygen, or let's see. That's true. You will not say monooxygen, right? Why will I start with oxygen on the left? Why? Yes, correct. Fluorine is more electronegative than oxygen. You can see from the periodic table, they are the same period. So oxygen is farther away from, as you go like this, fluorine is the most electronegative. So you know oxygen is less. So it's going to be on the left, the plus part, right? So in this case, even though you remember oxygen is always minus, well, when it's combined with something that is more electronegative than oxygen, then it's not going to be minus, it's going to be plus. And because fluorine is always minus 1, yes, times 2 minus 2, molecule 0, therefore oxygen has to be what? Plus 2. You see, very interesting, huh? Plus 2. Plus 2 for the fluorine there. And that's again the average oxidation number. In this case, the molecule is, the loose structure is symmetrical, so actually each one has plus 1. But that's not a time to talk about it. How about the peroxide? The peroxide, the oxygen in peroxide is how much oxidation number? Sodium is always plus 1 times 2 plus 2. Formula unit is 0. Oxygen has to have how much to make it minus 2 total? Minus 1, right? And here in this case, for this one, how much is the oxygen oxidation number? Always you have to say the sign. Unless it's 0. Always when this oxidation number, don't say 1 or 2 or 3. Always you must say the sign. Okay, so it's going to be what? Plus 1. Now you know to put order. Now, the good conclusion to come out of this is this, that the oxidation number of an element, the oxidation number of an atom, right, an element, in a molecule of polyatomic ion, it depends on the chemical environment. It depends to what it is connected with. So you can see, the different chemical environment, the oxidation number is different. For the simplest respect of these men, teacher will ask you to remain still. If you want to leave, and you don't really care about what your teacher will tell you, and perhaps some students, this half an hour, some singing, some songs, a little bit, some words. If you don't care, you don't need to feel like, that you have to stay or embarrassed. You need to do what you believe. If you don't believe on something, you don't have to do it. So if you don't care about what we're going to say, if the things about in memory of Martin Luther King, you don't want to have some songs, some maybe students will say something about this occasion, then you can do whatever you want. You can leave if you want. I hope you will not leave. I hope nobody will leave. Because that will show some understanding that when we lose our homes and jobs and we wonder why this is happening to us, perhaps we can find a way to remedy this situation, to lose the jobs tomorrow, to lose our homes tomorrow, to lose our beloved ones tomorrow, even to lose ourselves. Perhaps we will be able to avoid that by understanding the message of this man.
I'm hungry. Let's call that.
So if you are to leave,
let's call that.
good. If you decide that you want to stay, stay. Let's not waste time. Just are to leave, just go. Not to waste time. And then we're going to start the celebration, and we're going to continue the celebration at 8:10, up to 9:10, right? The room reserved until 10 o'clock, 8 to 10. 8:10 to 10 is reserved. So people will come with instruments, we'll sing, some maybe questions and answers. We're going to celebrate this day. Okay, so if you want to come back at 8:10, we'll be here. But we're going to do something now here also. This half an hour, okay? Are you settled? Are you the ones that decided that it is worth it to spend half an hour? And some of you might come later. Some people left, they might come back at 8:10. We cannot judge them. Some of them, they may come at 10 to 10. Who knows? Right? And they will stay more time than you. So we cannot judge them. We don't know how many will come back and be 2 hours later because they have to go somewhere. So we cannot judge them that they left. They might come back. And only just for half an hour, 20 minutes, but 2 hours. So you see, things are complicated. They're not as simple as we think they are. We start judging people. Isn't that right? Always, it's like the case. And that's something that really Martin Luther King's message is all about. His message, we know what it was, but we don't apply it. We can apply it every second of our lives. Even now, the mind can start judging these people they left and say, you know, they don't really care. But we don't really know if they care or not. They might have a plan to come back for 2 hours, more than what you will stay, and perhaps we will come back at 8. And we cannot make that kind of logic and attitude at the time that we have an unimaginable stockpile of weapons of mass destruction. We cannot afford to think that way anymore because the peril is too high. There is the so-called sword of Damocles sword on the head of humanity. At any time, humanity can be extinct. Something that we don't want to talk about, and many times we don't want to hear about it. And if we continue not to talk about it and not to try to change our way of thinking, instead judging, understanding, and waiting patiently, and resolve our differences with kindness and patience and humility, but we try to bomb each other, this world is not going to be around for too long. If we think it's going to be for too long, it's not going to be, unless we change that attitude. Which attitude is doing conscious judging, or sometimes even unconscious judging. There is a gossip. There is a gossip in us that's taking place continuously, and sometimes it's unconscious gossip. We don't even know we're doing it. It has become such a habit all the time to do it that we don't even know we're doing it. And that's very dangerous because someday there will be only a few people who will decide, should we do war or not? And those few that they will decide that, because we give authority to these people to do it, and we cannot blame them. Why we cannot blame them? Because we are the ones who give authority to them to make that decision. And if we're ignorant of what it means in our days, starting wars, it means that our leaders will not know either. So we have to educate ourselves very well about the peril that is in front of us. And in that way, the leaders that they come from within us, they are our husbands, our wives, our sons, our daughters, they will also know the peril. Because it is very dangerous to have people in authorities that all their life before they were playing video games. And they have never been in the horror of war. They have never seen blood. They have never touched blood. They do not know what war is. And most likely, such people tomorrow will make decisions of to go to war or not to go to war. And when we press that button, thinking that we're going to see on the screen a video game, because that's the only thing they will know. They were kids and they were playing video games all their lives. And now they are responsible citizens, authorities, that they will think by pressing the button, we will just see another video game. Then we are at the position of seeing whole humanity to live through an agonizing death. And that is what the so-called Russell-Einstein Manifesto talks about. It was worded about 50 years ago. It was signed by 10 names, 10 people that they were very eminent at their time. Among them was Einstein. Another one was Lenin. How would you say his name? Paul Lenin.
Paul Line.
Right? Who actually talked about the chemical bond. He really did a lot of work about the covalent chemical bond. And about vitamin C. He was in the peace movement. He was one of the major people to stop nuclear weapons testing. Unfortunately, we stopped them only on the surface. We continue to do it in the sea and in the caves. After we discovered there's strontium in every baby teeth around the world, we saw that we're killing ourselves. And that reason is that this gentleman, say loud his name. What's his name?
Linus Pauling.
Linus Pauling.
Yes.
He received 2 Nobel Prizes, one in chemistry and one in peace. There's only 2 or 3, maybe 4 from hundreds, probably more than 100 anyway, hundreds of them, Nobel Prizes. There's only 3 or 4 people that got 2. And he's one of them. I got 2 Nobel Prizes, one for peace and one for chemistry. Did you know about it? How many people in this class know about the so-called Russell-Einstein Manifesto? Let me see your hands. Almost none. You have to go and read the so-called Russell-Einstein Manifesto, which was signed about 50, 60 years ago by the most eminent people in science. And they warned every citizen of the world, all governments, that unless we stop resolving our issues with war, any moment, all humanity can go through an agonizing, extinctive death. And this document has been forgotten. This document is in the drawer. People around the world do not know about it. Governments do not know about it. They do not talk about it. Almost nobody knows about it. And now it's kind of a relative peace. After a few years, we might hear again all kinds of commotion. Oh, this guy there and that guy there and that lady there. Oh, no. And at that time, words do not suffice. People don't understand words at that time. They don't have patience. They are full of fear. This time that there is no such a thing happening, people, we, each one of us, must educate ourselves and understand the meaning and the message of the so-called Russell-Einstein Manifesto. Each one of you is responsible to go and read it and let other people know about the manifesto. Why? We celebrate Martin Luther King's Day. And his message was exactly the same like the Russell-Einstein Manifesto. Unless we understand each other, we are all on the same boat, with the same fears, hopes, and problems, and try to resolve our issues in a humane manner, the fate of humanity is in great stake as never before in the history of man. And any moment, within an afternoon, that face of the earth could be like the face of the moon. We have the capability, even as we speak, even by mistake,